Xiangnan. Hello everyone, my name is Xiangnan, and I'm honored to present our work, Non-Deterministic Face Mask Removal based on 3D priors to you. This is the outline of my presentation. I will start by giving the motivation and background for this research, and then I will talk about the related works. E.g., deterministic and non-deterministic face imprinting methods. Next, I'll present the three main parts of our research: the data, the model, and the loss functions. We have done qualitative and quantitative analysis that demonstrate the superiority of our method. Finally, I will summarize the main contribution of our research. People are advised to wear face masks in public to control the spread of COVID-19, posing new challenges for face-related computer vision tasks. Computers need to accomplish face recognition, expression recognition, landmark detection, etc. using minimal exposed facial textures. Restoring mask-occluded face textures is a promising method to be a one-step solution. To this end, we need to tackle two subtasks: first, detecting the occluded face regions, and then recovering the face textures corresponding to image segmentation and face imprinting, respectively. Face imprinting is an ill-posed problem. There may be different possibilities under the face mask: the expression, the identity, etc. So, in this paper, we propose a non-deterministic face mask removal method that can generate multiple, controllable, and non-deterministic results. The method closest to ours is this one, where we both focus on the problem of face mask removal and divide it into mask segmentation and face imprinting. However, they can only generate deterministic results. Some variational autoencoder-based methods can also produce non-deterministic outputs by sampling the latent code from predicted distributions. There are some other imprinting methods conditioned on sketches, facial landmarks, and even segmentation maps. Different from above methods, our approach are based on 3D face models, providing a dense and controllable prior for face imprinting. Next, I will talk about our method. Most mask-related approaches synthesize masked and unmasked training pairs by overlaying mask templates on face images of existing face datasets. However, as this table shows, the mask templates used by the previous method are pretty limited. Only a few tens of variations are far from sufficient to train a robust model. Therefore, we manually keyed out 900 masks from the masked face images and collected 800 textures patches to replace the textures of the original masks. The mask templates are then combined with the existing face datasets such as CLAV-A and FFHQ to generate data pairs on the fly during training goals. The proposed method is composed of a multitask 3D face reconstruction module and a segmentation module N3D and a face imprinting module NG. Given a masked face image IM, N3D predicts its corresponding 3D parameters from which a 3D face can be reconstructed and rendered, and also it predicts the occlusion mask M, indicating the mask silhouette. We then replace the mask texture with the noises based on M and guess IN, the noised occluded face image. Finally, the NG could predict the mask-free face image conditioned by the IN, M, and I3D. The predicted face is further fed into a discriminator to make it photorealistic. This is the loss function of the N3D. The segmentation task is solely guided by a binary cross-entropy loss. And the 3D reconstruction branch outputs a vector containing the face shape, pose, texture, and illumination informations. From this vector, it will reconstruct the I3D. To accelerate the training, we use the 3D coefficients predicted from the original unmasked face image by a pre-trained model of this paper. And so we get the ground truth of Z and simply calculate the L1 loss from the predicted one and the ground truth. We also leverage the photo loss, the pixel-wise photo loss, where M indicates the face area, and the identity loss, where F represents a pre-trained face recognition model. Here we use a pre-trained arc face, and the landmark loss for regularization. Finally, the 3D module, the N3D, is supervised by those loss functions together. Then I will present the impinging module NG and ND. The NG is a stack of residual modules, and ND is a VGG-shaped discriminator. So we use the following loss to supervise the impinging part: the pixel-wise loss, the TV loss to reduce the noise, the adversarial loss. So here is the qualitative results on the 3D reconstruction part. So accurately reconstructing the 3D face is the prerequisite for the success of the impinging module. Therefore, we first compare our method with the SOTA 3D reconstruction method. And thanks to the synthetic mask, the face images for training, our method is robust to face masks. And we compare our method with Zhang et al., a latent space sampling-based face impinging method, and Lafan landmark-guided face impinging method, and the method of Dan et al., the face mask removal method. Our method significantly outperforms others. The random sampling in the hidden space leads to apparent artifact in the results, as can be seen in this row. And in addition, for the landmark-based method, they need to provide the facial landmark by a pre-trained landmark detection module. For Ding et al., and we can find that their results are not very photorealistic. For example, the texture is not very well aligned, and the detection of the face mask is poor. There remains the edge of the mask part. And we also compare the face editing ability of our model with Lafan, the landmark-guided face impinging method. This time we provide Lafan with 68 facial landmarks extracted from our predicted 3D face model. This figure shows the result guided by different 3D priors. The first 6 columns are conditioned by different shapes, and the last column is conditioned by a brighter skin. As can be seen, with the guide of our landmark, LaFan can generate diverse impending results. Nevertheless, due to the sparsity of the landmark, the generated face do not precisely comply with the 3D face shape. In addition, LaFan cannot change the face skin as the last column, as we do. So we can change the 3D parameter to change the result of the impinging. We change the expression. Mouse. Okay. For quantitative evaluation, we synthesized 1,000 master face images on the test set, and then used LaFan and Zheng et al.'s method to recover the unmasked faces with externally provided binary mask maps. The face restoration ability is evaluated by the L1 loss PNSR SSIM cosine similarity of the identity feature and the FID. As can be seen, our method outperforms others in all metrics except the FID, where Ding et al. Reported a much better result. We have discussed this in detail in our paper. So in conclusion, we propose a novel 3D reconstruction guided mask removal framework that yields controllable results. The 3D reconstruction module was trained on masked faces to achieve high robustness, and we propose a large face mask dataset with an effective data augmentation method. So thank you for your attention.